In this video, we're going to start chapter 14. And chapter 14 is on acids, bases, and then also salts. There's three common theories for acids and bases. The Arrhenius theory, and I'm just going to list them here, and then we'll talk in more detail about each of them. The Arrhenius theory is the one that you would have learned in 130 high school. It was probably mentioned in 150, 151 also. We don't use it a lot this semester other than to remind ourselves what it is. It's a theory of acids and bases. If we're looking at neutralization reactions, I'll pull it out. But the bulk of the acids and bases that we're going to look at this semester, we're going to be using Bronsted-Lowry theory, which is actually named after two different people who are working independently. And then we'll also look at Lewis' theory of acids and bases towards the end of this chapter. If you go on and take organic, you'll actually spend quite a bit of time talking about Lewis acids and bases. So three common theories for acids and bases. Arrhenius first. So again, this is a very limiting theory. A lot of things that could be Bronsted-Lowry acids are not actually Arrhenius acids. So for this one, an acid is going to be something that's going to ionize in aqueous solution, so in water, to produce hydrogen ions. So if you put it in water and it forms ions, and one of those ions is a hydrogen ion, it's considered an Arrhenius acid. So this is going to ionize in water to produce hydrogen ions. H+, so hydrogen cations. So an example for us, if I was to take HCl, so hydrochloric acid, I'm putting an AQ after it, so it's in aqueous solution, right? It's in water. Remember, aqueous means it's in water. And then it's going to break apart, and I'm going to form hydrogen ions plus chloride ions, both of those also being aqueous. So because when I put HCl in water, I got H+ as a product, it's considered an acid under this theory. An Arrhenius base, this is going to dissociate in water to produce hydroxide ions. And this is honestly what makes this theory so limiting, is that the only way it's going to dissociate is to break it apart, and one of the products to be hydroxide is if it actually has a hydroxide ion. So this limits bases to only compounds containing hydroxide ions. So if I was to look at, and I'm just going to kind of write it down and then scribble it out in a few minutes. If I was to look at ammonia, ammonia is actually a Bronsted-Lowry base, but there's no way I can take ammonia, put it in water, and get hydroxide as a product, right? There's no oxygen over here. So there's no way I can get a hydroxide ion out of it. So while ammonia is a basic solution, it's not a base under this theory. So only compounds that contain a hydroxide ion can dissociate in water to produce a hydroxide ion. So again, a very limiting theory. So an example, we can use sodium hydroxide. Sodium chloride would not be an Arrhenius base, right? If I have sodium chloride, I'm not going to produce a hydroxide ion. So I get hydroxide ions and then sodium ions. It doesn't matter which order you write those in. So because I have hydroxide, right, as a product, when I put NaOH in water, that makes sodium hydroxide an Arrhenius base. I want to write, right, limits bases to compounds that contain hydroxide ions. We could write a similar thing with our acid, right? It's going to limit acids to compounds that contain hydrogen. Bronsted-Lowry acids also need to contain hydrogen. So if it's a Bronsted-Lowry acid, it tends to also be an Arrhenius acid. I do want you to notice that I used two different words here. So I used ionize for my acid, and then I used dissociate for my base. Any takers as to why I use different words there? Kind of to give you a hint, look at the nature of the acid and the base. So what is a big difference between hydrochloric acid and sodium hydroxide, right? They're both compounds, but what type of compounds are they? If you came up with that hydrogen bonded to chlorine is a covalent bond, so I could call it a molecule, right? It's a covalently bonded compound. And then sodium bonded to hydroxide is ionic, then great, because that's the difference. So kind of the reason I'm using different terms is remember, if we use our solubility rules, right, from the past, sodium has a positive charge. It is soluble in aqueous solution, and it's just hanging out with hydroxide in its negative charge. So the word dissociate, right, implies that they were associated. So I do have sodium ions, I do have hydroxide ions. When we put them in water, we're just separating those from each other. So I had ions and I'm separating the ions, so we can use the word dissociate. If I look at my acid, I don't have ions, right? Hydrogen bonded to chlorine is a covalent bond. I don't have H plus and Cl minus that are hanging out with each other that I'm separating, right? With sodium hydroxide, I have a cation and an anion. They're hanging out. I'm separating them. With sodium chloride, I don't have ions. So the word ionize, right? That means we're making ions from a covalently bonded compound. I'm producing ions from something that was not ionic. So this is not ionic, but we're producing ions. This is ionic, and I'm just dissociating them, right? They were associated, and I'm breaking them apart. So it is a difference. It's common to say dissociate when we're talking about acids. I'll do it often myself, but ionize really is the better word. It's the word that we should try to get in the habit of doing. So if it's not ionic and I'm breaking it apart into ions, right, I'm ionizing it. I'm getting ions from something that was not ionic. If it was ionic and I'm just separating those, I'm dissociating it. Bronsted-Lowry. And again, this is the theory we're going to use most often in this class. I will pull out other theories though, depending on kind of what aspect of acids and bases we're talking about. But an acid, according to this theory, is something that's going to donate a proton to another substance. And by protons, I am saying H plus. I'm calling H plus in the other theory a hydrogen ion. I know it's kind of confusing, right? We're saying a hydrogen ion and I'm writing H plus. Here I'm saying proton and I write H plus. It's the same thing, right? Just kind of as a little way of review, if we look at our most common isotope of hydrogen, it's hydrogen with a mass number of 1. Hydrogen has an atomic number of 1 if you look on the periodic table. So your most common isotope of hydrogen, right, would have 1 proton. Remember our mass number, this is my mass number, is the number of protons plus the number of neutrons. So because they're both 1, I actually have 0 neutrons. And then remember, if it's uncharged, the number of electrons are equal to the number of protons, right? The number of negative charges must equal the number of positive charges if it's uncharged. So if I was to remove, right, an electron from it to make a hydrogen ion, what I'm essentially doing, right, is I'm just getting rid of this, right? I now have 1 proton. I still have no neutrons, looking at my most common isotope. 1 proton, 0 neutrons, and I have no electrons because I removed it. So a hydrogen ion is just a proton, right? All I have is, right, a nucleus with 1 positive charge in it. I don't have any electrons. I don't have any neutrons. So writing H plus and saying a proton, that is correct. Okay, back to this. Sorry, I never finished writing it. Donates protons to another substance. A lot of times we'll just say proton donor, but it is important to note that it's to another substance. Bronsted-Lowry acids and bases are always going to occur in pairs. You can't give a proton to something else if you don't have that something else. And then that something else is going to be my base. My base is going to accept a proton or protons, H plus, from another substance. That other substance being my acid. I'm just keeping my tense or my plural and singular consistent. So an acid's going to donate a proton to something else. A base is going to accept a proton from something else. So these are always going to occur together. An acid's going to give a proton to the base. The base is going to take that proton from the acid. So Bronsted-Lowry acids and bases are always going to be paired. An example for us. And I'm going to use ammonia, NH3, as my base, right? It wouldn't be an Arrhenius base because I can't take NH3 and break it apart and get a hydroxide ion as a product, but it can accept a proton. When it accepts a proton, I get NH4 with a positive charge plus chloride ions. So NH4 plus, that was ammonium. It was one of the polyatomic ions that you were supposed to learn in 150, 151. So I do expect that you still know that. Ammonium ions. So kind of looking at these, the easiest way for me to determine if something's an acid or a base is to kind of look at the products. So if I look at the compound that contains chlorine here, it has a hydrogen attached to it. On the product side, right, the one that has the chlorine atom, chloride ions in this case, it doesn't have a hydrogen. So when I went, right, from here to here, we actually lost H plus, right? It donated a proton. So that makes this my acid. And then if I look at this one, oops, drew my line too far. Right, I went from nitrogen bonded to 3 hydrogens to nitrogen bonded to 4 hydrogens with a positive charge, making this my base. So the base accepted a proton, right? I had 3 hydrogens. Here I have 4 plus that positive charge, right? It's accepting H plus, not just H. And then if I look at my acid, here chlorine is bonded to hydrogen. Here I don't have a hydrogen, so I donated it, right? It lost it. So that is my acid. This gained H plus, right? My base is my acceptor, my acid is my donator. So essentially my acid gave that proton to NH3. That's how NH3 became NH4 plus and how HCl became Cl minus. Because they always occur together, Bronsted-Lowry acids and bases, we can define conjugate acid-base pairs. So every Bronsted-Lowry acid has a conjugate base. And then every Bronsted-Lowry base has a conjugate acid. And the conjugate acid-base pairs, so by pairs I'm saying this acid with its conjugate base, that would be a pair. And then this base with its conjugate acid, that would also be a pair. So every Bronsted-Lowry acid-base pair only differ by one proton and one proton only. If they differ by more than one proton, they're not conjugate acid-base pairs anymore. So conjugate acid-base pairs differ by one proton, H plus, and only one proton. And that's really important. So kind of an example. Are the following conjugate acid base pairs? And then I'll give us a couple examples. So we can do water and hydroxide, HNO3 and NO2 minus, H2SO4 and SO4 2 minus, F minus and HF. Let's do one more. HPO3 2 minus and H2PO3 minus. So when we ask this question, are the following conjugate acid-base pairs, what we're really asking is, do they differ by one proton and only one proton? That's really the question we're asking ourselves. So if I look at water, right, water is oxygen bonded to 2 hydrogen. And then I have hydroxide, which is oxygen bonded to 1 hydrogen and it has a negative charge. So do those two differ by H plus and only H plus? They do. So yes, these are conjugate acid-base pairs. So I'm going to let you do the others by yourself. Please hit pause. Again, what we're saying is we're looking at the pairs. Do they differ by H plus and only H plus? If they differ by something else than one H plus, then the answer is no. So give these a shot. When you're ready, hit play again and we'll go through the answers. Okay, hopefully you guys did that. So for B, I get no. They do differ by H plus, right? Here I have a hydrogen, here I have no hydrogen, and it has a negative charge. So if it was neutral, it lost a positive, so it's now negative. But they also differ by an oxygen, right? On this one, I have 3 oxygen, and this one I have 2 oxygen. So these guys differ by a proton and an oxygen. Right? It can only be by H plus. But go back up, only. So no. C, I also got no, right? These guys differ by 2 H pluses. Right? I have 2 hydrogen ions, right? 2 protons over here. Here I don't have any. This was neutral, right? It doesn't have a charge. This has a -2 charge because it lost 2 protons. So no, they actually differ by 2 hydrogen. If we go back up, they can only differ by 1 hydrogen and only 1 hydrogen. A yes for this one, right? The difference between F minus and HF is H plus, and then also yes for this one. More on conjugate acid-base pairs. I'm going to go up to this example that we had earlier. And I'm going to erase ammonium just so I have room here. So when your acid donates the proton, the species that's left is the conjugate base, right? We said every acid, if we go back here, every acid has a conjugate base. And we know that those pairs differ by H+ and only H+. So if HCl is my acid, Cl- is my conjugate base. I'm just abbreviating here, conjugate base. And then my base differs, right? My conjugate acid, I should say, differs from my base by 1 proton, right? Every Bronsted-Lowry base has a conjugate acid. They differ by 1 proton. So this is my conjugate acid. So those would be the pairs, right? This one and this one differ by H+ and only H+. Ammonia and ammonium ions differ by H+ and only H+. So let's write that in some words down here. So the species that results when the Bronsted-Lowry acid donates its proton is the conjugate base. And then the species that results when the Bronsted-Lowry base accepts a proton is the conjugate acid. A couple more examples for us. And I'm going to do this one a little bit differently. I'm going to tell us which is the acid and which is the base, and then we're going to write the products together, or you're going to write the products. So I'm going to start out with CH3CO2H, and we're going to react it with water. And this is going to be my acid. Acetic acid is my acid. And then water is going to act like my base. Water can act like a base and an acid. It can accept a proton or lose a proton. So what I want you guys to do is to write the products with the correct charge and then label the conjugate acid and conjugate base. So please hit pause, try to do that on your own, and then hit play again when you're ready. Okay, so hopefully you did that. Remember, our acid is going to donate the proton. It's our proton donor, whatever the right way to say that is. And my base is going to accept the proton. So I'm going to take a hydrogen ion, a proton, off of my acid, and I'm going to give it to the base, right? The base is going to accept it from another substance, that substance being my acid. So I'm going to have CH3CO2 with a negative charge, right? It lost that hydrogen and a positive charge. I now have acetate ions. And then my base is going to accept that proton. So instead of 2 hydrogens, I now have 3. Instead of being neutral, I now have a positive charge. Do note that your net charge on both the reactant and product side of a balanced chemical equation is always going to be the same. So if I look at my net charge, and this is a good way to check to make sure you're not missing something, I have no charge, right? I have a 0 charge, right? Acetic acid, this one has no charge. Water also has no charge, so 0 plus 0 is no charge. If I look on my product side, I still have a net charge of 0, and we're talking net. So acetate has a -1, hydronium ions, right? That's what this says, has a +1. A -1 plus a +1 gives me a net charge of 0. So the net charge always needs to be the same. And I would get in the habit of checking that because that's a really good way to notice if you missed something. Because if you write acetate like this, right, without that negative charge there, that's not actually acetate. It has to have that negative charge, right? If I was to write NO2, that's nitrogen dioxide. If I was to write NO2 minus, it's nitrite ions. Charges matter, and you need to show them when they have them. So just remembering that the net charge on both the reactant and product side need to be the same is a really good way to check your work. So if I left it like this, on my reactant side, I have no net charge. On my product side, right now I have a +1. So I know I goofed up because those two need to match. So then I would go back and I would check to see where I made that mistake. This needs to have that negative charge. So kind of use that as a way to check yourself. Okay. We still need to label our conjugate acids and conjugate bases. So my acid produces the conjugate base, right? That pair differs by 1 proton, and my base is going to produce the conjugate acid. Water and hydronium ions differ by 1 proton. Hydronium, it was also on the list of polyatomic ions that you needed to learn in 150, 151, acetate. Ions. Oftentimes I'll just say acetate or hydronium and leave the word ion off of it, but they are charged, they are polyatomic ions. Okay, let's do one more like this. NH3 plus HF, both of these aqueous. So same thing, because I need to tell you which is which. This is going to be my base, this is going to be my acid. So hit pause, draw the products, label the conjugate acid, the conjugate base, make sure your charges all make sense, and then hit play when you're ready. Alrighty, so my base is going to accept that proton again, so NH3 becomes NH4 plus. My acid is going to donate that proton, right? It gave it to ammonia. That's where that proton came from, which means I'm left with F minus. This is my conjugate acid, and this is my conjugate base. The conjugate acid will always have one more proton than its base. Right? If I go back up and I look at these guys, here's the base and its conjugate acid. Right? Remember, conjugate acid-base pairs are only going to differ by 1 proton, but they can differ by having an additional proton or having one less proton, right? The conjugate acid will always have one more than the base. And then our conjugate base will always have one less proton than its acid. And I forgot the word have up here. And I just kind of remember acids are proton donors. So the acid is always going to have that additional proton. Bases are proton acceptors. So the bases will always have room for one more proton. Right? My acid here compared to its conjugate base, right? The conjugate base has one less proton. The acid component has one more proton. So again, if I'm comparing these bases, the base to the conjugate acid, and then comparing the acid to the conjugate base, the two acids, right? Those are the two acids, are going to have one more proton than the conjugate bases do. The other thing to note about bases, remember protons aren't electrons, right? A hydrogen ion, we did this a little bit ago, right? I have one proton, I have no neutrons, and I have no electrons. Bonds are electrons, right? If my base is going to accept a proton, that base has to supply the electrons for that bond. So all of our bases are going to have a lone pair of electrons on them. If they don't have a lone pair, then they can't bond to that base. And that's kind of another way to check, right? If you were to draw the Lewis structure here for ammonia, ammonia's trigonal pyramidal with a lone pair of electrons. If I was to look at NH4 plus, it's tetrahedral and it doesn't have a lone pair of electrons. So if I just gave you those two, for example, if I gave you NH3 and ammonium ions, NH4 plus, and I asked you which is the base, which is the conjugate acid, or which is the acid and which is the conjugate base, if you have that pair, right, the acid always has one more proton, so this has to be the acid component, this has to be the base component, but you could also look at their structures, right? This one has a pair of electrons that can bond to a hydrogen ion. This one doesn't, so that one can't accept a proton, it can't possibly be my base. So another way to kind of analyze the two. So just an example, if I asked you to write the conjugate base for HCO3 minus, so bicarbonate ions. I know that a conjugate pair is going to differ by one proton, so I could either add one proton to it, right, H2CO3, so carbonic acid, or I could take a proton off of it, CO3 2 minus, carbonate ions. So depending on what I'm asking for, you're going to do either one of those. Since this problem wants the conjugate base, we know that our base will always have one less proton. So my conjugate base for this is going to be this, right, carbonate ions. I'm going to remove a proton. If I asked you to write the conjugate acid for HCO3 minus, this would be my conjugate acid of bicarbonate ions, or hydrogen carbonate, two names for the same thing. So again, my base component will have one less proton than its acid, and my acid component will have one more proton than its base. So an example for you guys to try, I have a table here, so please hit pause, copy the table down into your notes, and then complete the table. So the first column, I want the conjugate base of those things, so you're going to fill that in here. And then in the second portion, I want the conjugate acid of those things, so you'll write them in here. So again, please hit pause, write the table down, complete the table, and then when you're ready to check your work, hit play again. Alrighty, so hopefully you guys had some success at that. Our conjugate base, remember, is always going to have one less proton. So I'm actually going to take not less one proton, one less proton. I'm going to take off H plus from those. And then my conjugate acid is always going to have one more proton. So I'm going to add H plus to those. Remember, we're adding a hydrogen and that positive charge, right? I'm taking a proton, not just a hydrogen atom. And then same with the conjugate bases, I'm losing just the proton, the electrons are staying, so it's going to actually have a negative charge. So my answers for these ones, I have nitrite ions. This one, remember, conjugates, you're only losing one proton, so I'm only going to take one off. So bisulfate ions, or hydrogen sulfate. Sulfate, 2 minus. Water, right? Water is oxygen bonded to two hydrogens. When I lose H plus, I have hydroxide ions. and then chloride ions. And then again, the conjugate acid, I'm adding a proton to it. So ammonium, this is an amine. So I would add 3 hydrogens, and then I do have a positive charge. Add 1 hydrogen. It did have a -2 charge. I added H+, so it now has a -1, right? 2 minus plus 1 gives me 1 minus. Carbonic acid, and then water, we end up with hydronium ions. So to beat this completely to death, no one's gonna get this wrong. My base has 1 less proton than the acid, and my acid is always gonna have 1 more proton, and then again, they only differ by that 1 proton, right? They don't differ by anything else. So 1 proton and only 1 proton for conjugate acid base pairs.